Hi everyone, I'm Yuxin from Tsinghua University. We're excited to present our work ANSMET, Approximate Nearest Neighbor Search with Near Memory Processing and Hybrid Early Termination. Nowadays, vector databases plays an important role in search engines, e-commerce, and retrieval augmented generation. In those applications, searching for similar vectors is always the core operation in vector database. However, because current vector database has high volume of vectors and high dimensions, the efficiencies of vector searching can be quite low. So here comes ANS, Approximate Nearest Neighbor Search, which improves efficiency by organizing the vectors in a structured way, like vector indexing. Take HNSW as an example. It's a graph-based indexing algorithm widely used in ANS. It's called hierarchical navigable small words. The idea here is to traverse multiple layers of graphs, starting from an entry point here in the top layer. In the execution flow of HNSW, the entry point S0 is added to the search set first. During the computation of the search set, those vectors whose distance to the query vector is smaller than the threshold of the current result set will be accepted, or else it should be rejected. In HNSW, the threshold is the largest distance in the result set. So here, S2 is certainly accepted by the result set. Then S1 is also accepted because its distance is smaller than the infinite value. So as you can see, S2 and S3 are added to the search set because they are neighbors of S1, and S2 is accepted and S3 got rejected. Then S2 becomes the new threshold, and then S4 is accepted. So finally, the top two nearest vector to the query vector are S2 and S4. So from the demonstration, we can see that HNSW or ANS is composed of two main operations, which is graph traversal and distance comparison. Therefore, even if ANS has introduced the vector indexing, it still suffers from inefficiencies when running on CPUs. Firstly, it is still a memory-bound workload. Even with indexing, ANS still requires fetching many high-dimensional vectors. And secondly, distance calculations are relatively lightweight operations compared to the data movement. So ANS has low arithmetic intensity. For example, for those vectors with 128 dimensions, the arithmetic intensity is 0.125. Finally, our profiling confirms that 50 to 90% of vector fetching might be wasted because the distance of the vector is larger than the threshold and is rejected. So actually, we have used a lot of time to fetch the data that is finally rejected. So when talking about the first problem, the memory bump problem, applying ANS to near data processing hardware came up to us first. There are two major NDP types. 3D stacked NDP offers extremely high bandwidth, but they currently face limitations in the capacity due to the challenges of die stacking and thermal management. Compared to 3D stacked NDP, DIMM-based NDP incurs small modifications to the commodity DRAM architecture and can also support large capacity. Finally, we chose the DIMM-based NDP architecture for ANSMET. Applying ANS to NDP solves the memory bump problem, and it's also suitable for workload with low arithmetic intensity. However, the problem of low fetch utilization still remains, and introducing NDP will also propose the new demands of hardware support. So finally, there's a co-design called ANSMET. At software level, we propose hybrid early termination to enhance the fetch utilization. And at hardware level, we design supportive hardware, looking into the CPU and NDP cooperation and add some other optimizations to keep the workload balanced. Recalling the ANS demonstration, when traversing the neighbors of S1 and computing their distances, distance between S2 and query vector is smaller than the threshold and is finally accepted. But for the S3, the distance is larger than threshold, so it got rejected. So an idea came up to us. What if we add an intermediate between the real distance and the threshold? I mean, when fetching the vector data, before finishing fetching the whole information, we can actually estimate the lower bound of distance using existing partial vector. And if the lower bound is larger than the threshold, we can say that the distance is larger than threshold and we can reject the vector with partially fetched data. Take the following search and query vector as an example. The real distance here should be 10.247. What if we fetch 4 bits from the vector and judge it earlier? If we fetch the first dimension, we know that the distance is at least larger than the distance of this dimension when all those other dimensions are the same, which is 2. What if we fetch the highest base of each dimension? We can find a lower bound vector where each dimension is the closest possible value to the query's corresponding dimension based on the currently available data. Our estimated distance will be bound to be smaller than the real distance of this vector. For example, the first dimension of the lower bound vector should be the same to the first dim of the query vector. Well, for the second dimension, we know that the first bit is 1, so the nearest value to 0010 that begins with 1 should be 8, whose binary code is 1000. In this situation, the distance should be 6. Actually, those 4 bits can also come in a hybrid way. We fetch the first 2 bits of the first 2 dimensions, and we can also find out a lower bound vector following the bit level strategy, and the distance lower bound here is 10.198. So, as we can see, with different fetching strategy, the lower bound may be closer to the actual distance, which may help the search vector to be rejected earlier. So let's look into the execution flow. When computing the distance of S2, from the first to the fourth fetch, all of the estimated lower bound is smaller than the threshold, so the vector got accepted without any early termination. Well, when computing S3, on the first fetch, the lower bound is 6, still smaller than threshold, but for the second fetch, after finding out the vector that is closest to the query using the existing knowledge, the estimated lower bound is 10.198. It is larger than threshold. Therefore, we can early terminate it without the third or the fourth fetch. Now we have understood how early termination works. Remember that taking out which bit position first may impact the lower bound and further impact the time of fetches before we early terminate a vector. The key insight here is that not all of the bits contribute equally. Higher order bits have more impact but has lower entropy. So we fetch the bits from the highest to the lowest to observe the patterns inside. We can classify the bits into 3 regions. In the first region, the highest few bits often share a common prefix, so we should skip them quickly. And for the second region, those middle bits has diversity and are more likely to trigger the early termination. And in the third region, the lowest few bits have high entropy, but less impact on distance. Our strategy here is to introduce a pre-sampling stage and reorganize the data layout to fetch the most informative data first. Based on the first observation, we should skip the highest few bits if they share the common prefix. So we can eliminate the common prefix and enable the outliers. Here are 3 vectors, vector 0, 1, and 2. On the first step, we identify the common prefix using pre-sampling and find that vector 0 and 1 are normal vectors, and vector 2 has outlier elements. Then we use flags to label each outlier vector. And if this is an outlier vector, we use a bit inside each bit element to identify the outlier elements. And for those outlier elements, we insert the partially matched prefix length to the base of the elements, and also we store the full outlier vector elsewhere. And finally, we recover the outliers when searching. We can notice that there actually is a trade-off between the reduction of fetches and potential overhead for outliers. So actually, a longer common prefix doesn't necessarily mean a better system performance. Apart from the common prefix elimination, based on the first and the second observation that the highest few bits are less likely to early terminate, but middle bits are more likely to early terminate, we can optimize the bit or dim level fetch size based on the sampled bit patterns. When computing the distance of a search vector, for the highest few bits, we take coarse bit steps called NC for TC steps. In this case, in the first and the second fetch, we fetch the bits from the same dimension. The parameter of coarse bit step is 2, and the parameter TC here is also 2. Then, on the second stage, we take fine bit steps so that we wouldn't miss the bit that early terminates this vector. So on the third, fourth, and fifth fetch, we fetch the same bit position across different dimensions. So the parameter NF here is 1. To optimize those 3 parameters, we propose a cost model that uses sample data to find the parameter set that minimizes the total fetch cost. So after looking into the software optimizations that have enhanced the fetch utilizations, let's look into the hardware support for truly applying ANS to NDP hardware. As what we have noticed in the demonstration of HNSW at start, the workload characteristic is quite divergent. Index traversal is irregular and is of low parallelism, while distance comparison is regular and parallel. Therefore, we can conclude that index is more suitable for CPU and distance comparison is appropriate for NDPs. So, how to minimally modify the NDP hardware to support the distance comparison? Let's zoom into the DIMM-based NDP architecture. Each NDP unit has 32 query status handling registers, which is called QSHRs, which holds the metadata and task information. And beside the registers, there's a distance comparison unit that can recover the base and compute the distance in parallel. So here's the overview of current hardware design and workload assignment. Then how can CPU and NDP cooperate with each other efficiently? Firstly, we need to configure the instruction to set up the NDP parameters. Then we send up the query vector data to a QSHR in NDP from CPU. Then we should send the vector we want to search. In this demonstration, we should send up at 0. The CPU retrieves the completed results from NDPs by polling. After polling the results, the CPU stores the results to update the result set, and then traverses the neighbors of newly accepted at 0. Similar operations will be repeated until we get a final result. So we have explored additional optimizations to further enhance the efficiencies. For data partitioning, how to assign each partial vector to each NDP unit. Traditionally, there are 2 strategies. Vector partitioning contributes to parallelism but needs CPU aggregation, while horizontal partitioning may lead to load imbalance. For the hybrid choice, we can split it into sub-vectors and assign it to different ranks. ANSMET finally chooses hybrid partitioning and keeps the vertical vector size large because it could help with early termination. What's more, ANSMET replicates hot vectors to different ranks to further enhance the workload balance. Another design point here is adaptive polling. As we can remember that polling is the action that CPU checks the registers from NDPs to retrieve the results. But early termination makes the latency unpredictable. So adaptive polling is proposed to ask CPU to calculate the expected latency based on sampled early termination frequency, improving the response efficiency. We simulate using Remulator version 2. Our setup uses 4 channels, 2 DIMMs, and 4 ranks, with 32 NDP units. We test across 7 frequently used datasets. We run on both CPU and NDP configurations. We run baseline first and then added simple early termination, then added data layout optimizations, and finally the full ANSMET design. We also compare our design with previous early termination schemes. We have 5.26 times speed up after adapting the NDP hardware. The memory access is reduced by 25.1% after introducing the simple early termination. We can get 1.52 overall speed up after taking the whole ANSMET early termination strategy. It has been a significant speed up compared to the dimension or bit-only early termination, and here is the whole comparison. And as for energy consumption, we have saved 85% energy in total. In summary, this is our work ANSMET. We propose the first DIMM-based NDP system to accelerate the NAS with a novel early termination strategy. Thank you for listening and looking forward to your question.